In this exercise we will create this model, number 1. Very important thing is to start building it inside SolidWorks as a part with the IPS units. When you type dimension, after 11, type FT, which will automatically convert it to 11 feet. There is also a node here, so it needs to be aligned up to a middle, otherwise it will create an unstable solution and geometrically impossible solution in a plane. The key here is to identify the proper supports, and this support on the left, the node F, it needs to be constrained in all directions. By the right support, the node H, it will be free to move along global x-axis. You will start making this model on the front plane in SolidWorks by making the linear 2D sketch. After that you will go into welding structural members and you will build out the frame using the structural members, following simulation setup. So let's now start SolidWorks and let's start building this piece. In a SolidWorks we will start a new part. And the first thing that we will do here is we will set that our add-ins, which is the SolidWorks simulation and SolidWorks toolbox for generating frames, are all checked in as they are here. We will click OK. We can set up the material, so not to worry later, and we can take like alloyed steel for now. And we can set the units, tools, options, document properties, units. I will set up units to IPS, and I will put a 3 decimals, as well as here 3 decimals. Angles are 2 decimals, that's okay. Click OK. Next, what you will do is you will start now making the sketch. So click on a sketch submenu, click on a sketch and choose the front plane. First thing that we will do, if we look back at our structure, we have a 1, 2, 3, 4 times 11 feet line segments, and here we have a 2 11 feet line segments. So this is our bottom. So let's go back to our CAD. Let's start to constrain the model. Let's start line from here to horizontal line. And now let's put the dimension to this horizontal line. And remember that this is in the inches, so you will need to type in 11 FT, what means foot, and press enter. And 11 feet is 132 inches. Now we need another line here for the bottom, and we started drawing this model from the bottom. Another horizontal line, and that line is going to be also 11 FT, 11 foot. Don't forget to type the FT. So you can see it automatically changed. 9.6 foot is the vertical member size, so we are now going to put those. And we will have 3 of them, so it's easier just to make the one. Again, we are just going to type it 9.6 FT. Now, what we can do the linear sketch pattern. We can choose this one. We can say that the distance is a 132, and we can change this number to 3. And click OK. Here are our lines. They are defined, that's fine. Now we can put the top lines to close them. And we can put another line segment from here. It's of crucial importance not to draw the long lines. Each segment, each physical segment, need to present by one line of the determined length. Otherwise it will become a beam model, not the truss model. We also know that there is a here horizontal line of 11 foot for this member. And we also know that there is a member here of the same. FT. And we know that those two are connected with a diagonal member, as well as on the opposite end. And now we need to make the cross member in a middle, and we need to break those in a center. So let's see how can we make those. The easiest way to make those will be if we already create a center line which will have a midpoint, and now just stretch the line from here to a midpoint back, and you can either continue building line or do the mirror entity. Let's build one and then maybe mirror it. Or we were also able to mirror this one too. Okay, if we do the mirror, entities to mirror 1, 2, 3, 4, and mirror about this line. And mirror always do some conflicting elements, so let's see what is the conflicting items here. However, then it will create another set of problems. So for this case it's better just to continue drawing it. And here is our model completed, our structure of the model. And as you can see here, it is fully defined. Now let's build a physical object out of it. Click on the Features menu, go to Insert, Weldments, Structural Member, and we can choose whatever. We can, let's say, rectangular tube or square tube and size, or we can select ANSI inch size, and let's select the tube, maybe square tube, and let's say size 4x4. And now the first group that we are going to create will be the outside members, and that group will contain all of the outside member frames. Then you will click a new group, and in a new group you will create, for example, another closed pattern. Let's see which will give us the because I believe that this can be made just by making 3 groups. Okay, that's our group number 2. And the last group, as I said, you can economize with a group. Group number 3. And the last one will be this group here, single stabilizing gun. If we click OK, this have now created a nice looking frame in a space weldment structure. Let's save this. For example, problem 2-2. Now we are ready to move to the simulation tab and to click under the study advisor and to click on a new study. When you click on a new study, it will ask you for a type, and we will click on a static type. Click OK, and it will generate now. And it will generate the stuff. Here is the problem which we say the beams. However, it is not a problem, because when you click here, we are going to select all the elements, and we are going to explicitly specify by clicking on edit definition that those are not the beams, that those elements are truss. And then if we go to a join group and we click on edit join group, we can say to recalculate the joint group, and we will need, as you can see, because of the numerical inaccuracy, here we have a problem that we have like the true unconnected joints. So actually we can select here, let's say everything that is less than 3 inches will be a single node. So let's see, you have now 3 nodes which are completely error nodes. Let's see if I recalculate. Click OK. Let's see what we have here now. They are still separated, so we will do the edit group again, and I will put like here maybe 10 inches. All. Joints are. Aha, look what happened. As we increase the spacing for a single joint, those meter cutted elements were joined together. So now if we check this structure, you can see that every single joint is correct. What is the next step in analysis? Is to set up supports. And if we look at the picture here, the left support is fully constrained, and the right support can move along x-axis. To set up the support, we will go to a fixture, say either from here or from under fixture advisor, and click on a fixed geometry. And I will click on a fixed geometry and click on this node. Click on this joint, click OK. And now I'm going again to go to a fixed geometry, and I'm going to use the reference geometry to define that this one is free to translate in X as my reference plane. For the orientation of the coordinate axis, I will use the front plane. As my node, I will use this node here. And now, what I'm going to do, I'm going to specify that it cannot move out, that it cannot move in and out of our plane, and it cannot move vertically, but it is free to move in an x-axis. It's free to move along the x. Press OK. Now, what we need to do else? We need to specify for every single node that it can't move in and out of our screen, because it is a 2D model. That way, you constrain it to be a 2D. So, again, we go under the fixed geometry, and again use reference geometry. Reference geometry will be a front plane. This time we will only constrain normal to the plane, so essentially in and out. And we are going to select every single node except the nodes that we already did. So we'll select this one, this one, this one, this one, this one, then go down, select this one, and finally this one. Press OK. Now, if you zoom in, you can see something, and if we rotate, you can see that this one have like this node on the left is constrained in all directions, by the node on the right support is constrained only in and out of plane and vertical, and the rest of them are only in and out of plane. Now, the final thing that we need to do in this model is to add this force of 4,800 pounds. So to do that, let's go back to isometric view. You will go under external loads, you will click on a force, you will choose the IPS English, this is unbelievable. And this happened, that it kind of just... Next thing in our model that we have to do is to add the forces in the proper locations. And if we look at our model, it's 4.8 kips, what means 4,800 pounds at every of those nodes. You add force by adding external load, force. Click node, very important. Click reference, front plane. Click units, English. Well, again SolidWorks. Alright, so here in this menu for the force, what we did, we choose all of the joints, we choose the values of the force and direction and click OK. What will set up our model? And let's see something else in a problem 2.2, the units. If we go to a tools, options, document properties and units. Units should be in IPS units. So now the model is ready for simulation. And how we are going to simulate it, we will press run. And here is the model. It's done. So it works. And here is the deformation of the model that you see, which is kind of an intuitive displacements. If we go to an edit definition, We can choose the units now here to be like inches, for example, for a displacement. And for the stress, edit definition, we can choose the units to be in a PSIs. And now you want to see the results option, you want to see at the results folder. If you click right, really only what here is meaningful is to list result forces and to list the beam forces. Let's see the resultant forces. Again, the reaction should be on the front plane in a relationship to the front plane. And the nodes that we are looking for are, of course, this node and the other node. And here are our results. And let's change this to a IPS, to a pounds. Okay, so the only real resultant force should be vertical. And what is this? 12,000 pounds. 1.2 E on plus 4 pounds. Okay, so in vertical direction. And here, 1.2 times 10 on fourth, so 12,000 pounds, so evenly distributed. This was obvious case that it will be evenly distributed because model was fully symmetric. Now, what else can we get here? We can get also, by clicking on a results, you will list the beam force, list the member forces, and we want to list forces. And if now we look into each of the elements, the structure, remember we can see that the simulation is correct. There is no other forces than axial forces. And we can find into which structural members we have the highest force. And again, you will switch to the IPS. And find me the element. Where is the element number 7? If you click on it, it will show element number 7 is 32,472 newtons. So that's the element with the highest force. Let's see if we have some elements which have a zero force. What do you think? Should there be any elements with a zero force? We don't really know, maybe. Stabilizing elements. In a units. There is no one with a zero, so all of the elements, all of the members, all of the members of this group have the loading capacity, as you can see. All of the members carry the loads. And if you click on particular one, it will show you which one it is. You can also export these values by clicking Save. You can export this as an Excel file. And you can export this as an Excel file, which then subsequently you can open in an Excel. Here is the names, and here are the values in a pounds. As you can see, this is a pretty symmetric situation, like 2804 and 2804, because we have a symmetric structure. So, and this will conclude this exercise. So these results will conclude this exercise.